This conference will now be recorded.
Very good evening to all of you students. Welcome to the PYQ discussions. As you know, we have been discussing the numerical problems from the question papers of JEE Mains 2024. Today we will be discussing few questions from JEE Mains 2024 5th April shift 1, shift 2, and also some questions of 6th April shift 1. Okay, so let us start our discussions for today. So as you see, this question is actually from dimension analysis from the very first chapter. So here the question was the dimension of square root of g and mu, where g is universal gravitational constant and mu is energy gradient. As you know, this g. So how do we know g? G is equal to F into R square by capital M and small m. Okay, so this is gravitational constant. So if I want to find out dimension of this, so I get, so dimension of force ml t to the power minus 2, and here there is r square. This is also distance square, so it will be ultimately l cube, and here see there is m square down, so it will be m to the power minus 1. Okay, this is the dimension of g. All right, now what is mu? Mu is actually energy gradient. So energy gradient, it is not mentioned properly what is like gradient of what. Energy gradient means like velocity gradient, velocity with respect to space or distance, v by d. This is velocity gradient. Similarly, if I take energy gradient e by d, okay, that means energy changes with distance. That is the thing, and like everywhere that energy is not same with respect to space. That is what is energy gradient. Now energy, I know this is force into displacement, so m l t to the power minus 2, and displacement so into l, so that will give you m l square minus t to the power minus 2. And see here you have in the down you have another distance. Okay, so l, so ultimately what we get here, we get m l t to the power minus 2. Okay, so you look, I have been given to find out the dimension of square root of these quantities. Okay, square root of these quantities. Look then, see this one, let me multiply here, m to the power minus 1, l to the power minus l to the power 3, t to the power minus 2, and see here this is m l and t to the power minus 2. So look what I'm getting, this m to the power minus 1 and m, they will cancel each other. So what I'll get ultimately inside the square root, that is l to the power 4 and t to the power minus 4. So this will give you l square t to the power minus 2, sorry, let me write it properly. So what I'm getting, l to the power 2 and t to the power minus 2. Okay, so option B will be the correct answer for this question. So here excuse me, so here this mu energy gradient, this is where you might be stuck up. You have to understand when you don't have been, like, you are not given the gradient. Energy gradient means what? Then you have to take in that way energy per unit length. Okay, now this is an interesting question. So the question says a block of mass m, that is 50 kg, is lifted from the ground into a height of 20 meter in two different ways as shown in the figure. Look, so this m is directly lifted from ground to this much height. Okay, and in another case it is actually pulled like this up to here. Okay, so question is, find the work done by the gravity in both cases. Find the ratio of work done by the gravity in both cases. So this case, I know work done by the gravity will be exactly equal to the work done against the gravity. So that is mgh. Okay, right? So this is very nice, isn't it? Like, this is very simple. I'm not putting the values. Let me just write like this itself. So in first case, let us say this is W1 when we are just lifting vertically straight away. Okay, but when it is pulled up to that height, see this height is actually h, that is 20 meter itself, but I have used an inclined plane to pull it up, right? It is difficult to take, like, if you just uh, take some load or some weight in your head, like on your head, and walk on a very steep staircase, that will be little difficult. But if the staircase has a good amount of inclination, then you don't feel that much hardship. Okay, that much hardship you don't feel. But what about work done in both cases? Whether work done is more in this case, like in the first case, or less in this case, or work done will be the same. That is what we have to find out. So let me take the length of this inclined plane to be L. Okay, and this height we know. Let me take this height as h, as I have taken in the case of, like, in the first case itself. H is the same. Now you know, when I'm just taking it to the up, I have to work against the gravitational force, and that gravitational force is not exactly mg, that is mg sine theta, as you know. Okay, I hope you know this, but still I'll just show you how the gravitational force acting on this body along the inclined plane will be mg sine theta. Look, if this is mg vertically downward, and this is, since this is theta, you know, so this will be, sorry, 30 degree, this also will be 30 degree, right? And look, this is n. Okay, so this will be mg cos theta, cos 30 degree, right? So cos 30 degree, and this will be mg sine 30 degree. Okay, this is mg sine 30 degree. So I have to see, if I take this length of the inclined plane to be L, then I know the force against which I have to work. So that is mg sine theta. Sine theta means I'm taking sine 30 here. Mg sine 30, that is the force against which I have to work, into the displacement L. Sorry, this L. This is L. Okay, the length of the inclined plane. So this is the work done in the second case. Let me show you that this also will be same as W1. How do I do that? See, I have got a right angle triangle down. So this side is L, suppose, and this side is H, and this is this. So what will be sine 30 degree? What will be sine 30 degree? Sine 30 degree will be perpendicular by hypotenuse. So what is L sine 30? L sine 30 will be nothing but h, small h, isn't it? So I can write this as small h itself, right? So look here, the work done in both cases actually will be the same. Work done in both cases will be the same. Work done in both cases will be the same. So in this case also it is mgh directly, and in this case also it is mgh, where L sine theta is nothing but h itself. Okay, isn't it? So that's why W2 by W1 or W1 by W2, that will be 1, right? So the ratio will be 1:1. I hope you have understood this. Let us go to the next problem. Okay, this is very interesting problem. Look, in this question there are two concentric conducting rings of radius A and B are placed as shown in the diagram, where A has got lesser radius than the B. That means the bigger one is having radius B and the smaller one has radius A. Find the coefficient of mutual inductance of the rings. So how do I find out mutual inductance? So to find out mutual inductance, coefficient of mutual inductance, what I have to do? I have to find out flux. We know flux is equal to mutual inductance into I. I is the current. Okay, I is the current. That means what? See, if I pass current in the bigger ring, okay, if I pass a current in the bigger ring, it will produce a magnetic field at the center, or it will produce magnetic field anywhere right inside. So that magnetic field will actually induce, or magnetic flux will be connected to this smaller ring. Okay, right? So then what I have to do, I have to just get pi by I to get the coefficient of mutual inductance. This is the thing. So in any case, you need to find out coefficient of mutual inductance. You just find out what is pi and then divide that with I. Okay, that will give you the coefficient of mutual inductance, right? So in this case, let me tell you, see, I'll just write some notations over here. Let me write down here. Suppose pi A B, that means, you know, flux linked with A due to current in B. Okay, so this is what it is. If I write pi BA, anyway the value of the coefficient is going to be the same in both cases. If I find out the coefficient for, see, this mutual inductance, coefficient of mutual inductance means they have the common coefficient, okay, common value of M. Okay, so I can find out pi AB and then divide the current in B, okay, current flowing through B, or I can find out the flux flux linked, let me write it, flux linked with B due to current in A, current in A. Okay, I hope you are understanding. That means, see, pi AB means when I pass current in the bigger ring, then it will produce a magnetic field, and that magnetic field lines will passes through this, right? If I have a loop like this, and suppose my magnetic field lines are passing, uniform magnetic field lines are passing like this, and suppose the strength of the magnetic field is B, and I know the area of this loop is A, then phi will be B into A, right? If the magnetic field lines are passing perpendicular to the area of the loop, then I can write this, isn't it? Otherwise I have to take component, that is different thing. But the main point is here that the magnetic field has to be uniform. That is main point over here. Okay, if the magnetic field is not uniform, then you cannot do this one. You have to do certain integration or something like that, because the magnetic field is not uniform. So place to place it may vary. In that case things will be little difficult. So my point is here is that the magnetic flux you are calculating with a particular loop or ring, the magnetic field which is passing through the loop should be uniform. Now let me tell you why I'm saying this thing. So I have knowledge of finding out what is magnetic field and magnetic flux, magnetic field for a ring, those things are fine. Now if I suppose I want to find out what is flux linked with A, so what I have to do, I have to find out the magnetic flux A. Okay, magnetic flux AB, then mu AB into IB. Okay, that means when you pass current through the bigger ring of radius B, you have to calculate the flux linked with the A. And if I write phi BA, that means you are finding out flux through the bigger ring when the magnetic field produced by A. Now which one to find out here? Eventually this MAB and MBA will be the same, but which one to adopt over here? Which flux I should calculate? Do I find out magnetic field due to this one? That I can do, but look, if I draw the magnetic field lines over here, you know, look like this. Suppose, okay, so let us say current is flowing like this in this direction. Sorry, in this direction. Let me take the color of this pen to be red or some other color so that I can indicate. This is a very nice question actually. Let me draw the field lines over here so that, let me suppose in the beginning I am just taking the current in this direction in the smaller ring like this. Okay, sorry, I'll take just opposite like this. Okay, so like this. So here the field lines, if I draw, it will be like this. Okay, like this, like this. In this case it will be like this. See, the directions will be in this way, like this. Okay, and in this case it will be like this. Okay, so like this it will be. Okay, so you can see here, if I consider the magnetic field like this, it will be this like this. Okay, so flux link with this bigger ring will be there, but you know it will be really very difficult to calculate it because the B is not uniform. B is not uniform. Okay, is not uniform in this case. Okay, if you draw the field lines properly, you can understand that. Okay, like say magnetic field lines will be like, see, for a loop how it is. Just I'll show you here once again. Just for a loop, single loop, suppose this is my loop. So how you get magnetic field lines are like this, right? And in this case, this side it will be like this. Okay, so ultimately the uniform magnetic field will not be uniform. Okay, but if you have symmetrically uh, multiple rings, maybe you can create uniform magnetic field for a single loop. It is very difficult to get uniform magnetic field. Okay, but then I'm not going with this first one. Okay, I am not going to calculate the flux linked with the bigger one. Rather, I'll calculate this one. Okay, so this will be difficult because magnetic field produced by the smaller ring will be not uniform throughout the area of this bigger ring. Okay, but look, in this case, in the other case, when I calculate magnetic field produced by B, see, suppose this produced by B at the center, see, near the center, you know, the magnetic field lines will be nearly uniform. I'll tell you why. See, magnetic field lines, like it will be like this, right? So you will see some lines like this. These are uniform, like nearly uniform. Okay, through this small area. Okay, since this is much greater than, see, A is actually much less than B, so the magnetic field created at the center, near the center, or at the center of the bigger loop will be nearly uniform for the smaller ring. Okay, so that is why it is easy to calculate magnetic field, magnetic flux linked with the smaller one. Okay, so I can find out, see, this one pi AB flux linked with the inner ring. So magnetic field produced by B into pi a square. Okay, so magnetic field at the center of a ring is mu naught I by 2a, 2 into area, sorry, 2 into the radius. So in this case radius is B, right? 2b. Okay, and see, this is pi a square. So what will be phi, m? See, if I write this, mu naught I, mu naught pi, mu naught pi a square by 2b into I. Okay, this is I, obviously this I is through B. Okay, so this is actually phi of AB. So what will be m of AB then? That will be phi of AB by this. Okay, so this is the thing. So look, MAB, or coefficient of mutual inductance, will be mu naught A, sorry, pi a square by 2b. Mu naught pi a square by 2b. Mu naught pi a square by 2b. So B will be the correct answer for this question. All right. Okay. Let us go to the next problem. Okay. So this problem is very, very simple problem. So here you have to find out the current I in the given circuit. See, this is the current. That means the total current in the circuit you have to find out. Look, if I draw the equivalent circuit diagram, then you will be thinking how easy it was. See, this is 12 ohm. This is the battery, 12 volt battery, and this is the current I. Okay. Look, this part, this is a conducting wire. So there is no potential difference between these 2 points. That means what? I can take these 2 points as identical point. That means this 4 ohm resistor is connected to a, see this itself. Okay. 8 and 4 resist 4, even this 8. See, these 3 ends are actually connected at the same point, I can say. Okay, now look this one. This is a conducting wire. This is a conducting wire. So there is no difference in the potential here, here, and here. Okay, that means what? So this, see this resistor, this one, all three are connected parallel to each other. Okay, so I can write here. Okay, all three are connected parallelly, and this combination is connected in series with the 12 ohm, and this is the whole thing here. So this is 8 ohm, then middle one is 8 ohm, and the outer one is 4 ohm. So I have to find out this one first. So 1 by R equivalent is equal to 1 over 8 plus 1 over 8 plus 1 over 4. So here I'll get 1 plus 2 divided by 8. So R equivalent will be 8 by 4, that is giving you 2. Okay, so I get equivalent resistance 2 out of this 2 ohm, that is connected to the circuit in series with 12 ohm. So what is the ultimate resistance in the circuit? That is 12 plus 2 ohm. That means the total resistance, equivalent resistance, is 14 ohm for the circuit, right? So now let us erase this point. So what is the current? Current will be V by R, right? V by R. So what is V? V is 12 volt. And what is R? That is 14 ohm, right? This will give you current in ampere. Okay, that is 6 by 7 ampere. Look this option B, which is correct answer for this question. Okay, so guys, it was very, very simple problem, and this is actually from shift paper 2. Okay, shift 2, sorry, 5th April shift 2 paper. This is also the question from the paper 5th April shift 2 paper. The correct relation between the kinetic energy and the total energy of a satellite orbiting around the planet. Look what I get. Suppose there is a planet orbiting around. Okay, so you know I'm sorry, let me just take this and let me take a satellite here. Okay, satellite, it is orbiting. Okay, this is, suppose this is the orbit. Okay, radius, orbital. So this is the radius of the orbit, and there is a planet here. Okay, I have not drawn here. Let me take this as point itself. Okay, so center to center distance between the planet, if I would have drawn like this, I'm sorry, I can draw it here, no problem. Okay, suppose this is Earth and this is Moon. Moon is the only satellite for natural satellite, obviously only natural satellite for the Earth. Okay, let me take the center to center distance to be R. Okay, so I know I have to find out what is kinetic energy of this, okay, of the satellite. So I have to find out, suppose this has got mass small m and this has got mass capital M. Okay, so half m v satellite orbital velocity, v orbital square, right? And there it will be, this is actually obtained by, this is actually, I'm sorry, this is kinetic energy I have to find out. Okay, but if I remember what is v orbital, then it is very fine. Otherwise I can find out what is orbital velocity. Let me write down, see, m v orbital square by radius is equal to the gravitational attraction. Okay, the gravitational force is actually supplying the centripetal force for the, or sorry, for the circular motion of the, or rotational motion of the satellite, isn't it? So g capital M small m by r square. Okay, so okay, so in this case, obviously this is this height, if I take h, okay, so here it will be a little different. Let me just write g mm by r square. So center to center distance, that is fine, but this radius will be, okay, for the time being, let us take this in this way itself. Otherwise I can go for, okay, so center to center distance is this one. Okay, so this is height. Excuse me. So this height, if I take this height of the satellite is very near to the earth surface, in that case I can write this one. Otherwise I have to write r minus, if this is the height, so I have to actually write mv square by r. This r has to be written as, yeah, I think this is all right for the satellite which is very near to the earth surface. Okay, so this is fine, just to get an idea. Okay, so here I can write this. So from here, this r, see, look, this is, okay, so this is actually the orbital velocity. And what is this potential energy then? So this is, I'm sorry, this is total energy, right? This is total energy. So total energy means kinetic energy plus potential energy. So what will be the potential energy? So g m, potential energy will be g mm by r. Okay, this is potential energy. Okay, and what is kinetic energy? I have got half mv orbital square, so that means gm by gmm by 2r. Okay, so these are two energies which I have to add to get the total energy. Total energy means potential energy plus kinetic energy. So this will give you actually minus of gmm by 2r. If I take mod of this, so I'll just take positive of this. That means, you know, this is gmm by r. See, this is gmm by 2r. This is the kinetic energy. Okay, so this is nothing but kinetic energy, right? So this is kinetic energy. So if I take the modulus of total energy, that will actually give you the kinetic energy itself. So the first relation between kinetic energy and the total energy will be the same. Okay, so this is very nice question. Sometime, yeah, so this kind of question comes in the exam. So as you can see, this was the question of 2024 JEE Main 5th April shift 2. All right, very nice. Now we'll go to the next problem where we have to calculate the energy release. That means the energy released in nuclear reactions. Okay, see, 3 helium, this is energy due to fusion. Okay, 3 helium atoms from carbon at high temperature due to fusion. Not carbon, I'm sorry. Yeah, so 3 helium atom form, this is not from form carbon. Okay, so suppose there are 3 helium. As you know, helium is actually 2He4. 2He4. So it has mass nearly 4. Okay, so if I take 3, then I'm getting nearly 12. So that is having, like, carbon has mass 12 as well. So that's why, suppose there are 3 helium which are fused at very high temperature, to form a carbon. Okay, carbon 12. See, the mass of helium, each helium is given 4.0002, and this is 12. This is the mass of the carbon. That means, you know, if I find out the mass of this all three, total mass of all 3 helium, I'll get 12.0006. This is actually in the atomic unit, atomic mass unit, right? What is the mass of carbon? So this is mass of the product, sorry, mass of the reactants. Okay, reactants. Okay, mass of the product, is just 12 mu. So from here, what I can say, there is a loss of mass, or there is some extra mass which is actually vanished, but mass cannot be vanished, right? So there is a mass energy equivalent formula, or conservation, mass energy conservation. So mass conservation is there, energy conservation is there, and also in high energy physics there is something called mass energy conservation as well. Mass energy conservation. That means what? When a mass disappears, that gets converted into equivalent amount of energy. This is called mass energy conservation relation, or mass energy conservation law. Okay, this was actually given by Einstein. Okay, so that you know that very well, E is equal to mc square, the very famous, it is actually delta mc square. Okay, so change in the mass will actually gets converted into energy. Okay, energy. So the loss of this mass 0.006 amu, that much mass will get converted into energy, and which will actually released in this process, Okay, so by mass energy conservation law, I can find out the energy release. Energy released in the process as delta m, the mass defect, into c square. What is the mass defect? That is actually, since it is given in terms of mu, so I can actually find out delta m into multiply 930 or 931, whatever. So that will give you in MeV unit. Okay, so if you multiply 0.0006 with 930, this will give you something like this. Okay, 0.56 MeV. All right, so this will be the answer. Okay, option B will be the answer for this question. All right, so let us go to the next problem. So this is also from SIP 2 paper. The question says in YDSE, that means Young's double slit experiment, wavelength is given lambda. Let me write it here. 5000 angstrom. This is angstrom. That means, this is 5000 into 10 to the power minus 10 meter if I want to convert into meter. Slit distance, that means small d. This is given as 3 millimeter. That means 3 into 10 to the power minus 3 meter if I require to convert it into meter. The screen to source distance will be, see, screen distance is given capital D as 2 meters. The intensity at a point which is 3 centimeter away from the central maxima. Assume intensity of light of each source is I naught, is x into I naught. Then what is the value of x? See, the value of x I have to find out. See the question here. Suppose I have double slit arrangement. So small d is given, this capital D is given, lambda is given. Now in case of YSD, see, all will be having like this. Okay, like this. Okay, the intensity pattern. Okay, anyway, so what I'm trying to say is that you have to find out the intensity of the light. See, if all the bright pattern, I should say all the bright fringes will have the same intensity, all the dark fringes will be having almost zero intensity. Okay, that's what I can say. If suppose this is the central one, then the other one also will have the same intensity. Okay, same intensity. Okay, this is the beauty with intensity pattern. But in case of diffraction, there will be dying intensity for the bright. That's why we say principal maxima and secondary maxima. Okay, or the central maxima and the secondary maxima. Okay, that is what we say. Minima, we say first minima, second minima. So in this case, I have to see whether the point which is 3 centimeter away from the central range. Suppose I take this as y is given as 3 millimeters, 3 centimeter. 3 centimeter, this much distance at this particular position, whether it is bright position, bright fringe, position of bright fringe or dark fringe. So that is what we need to find out. So for that, what you have to find out, we have to find out the phase difference. Okay, delta phi. Delta phi means 2 pi by lambda into what? 2 pi by lambda into path difference. So we need to find out what is the path difference at a point which is 3 centimeter away from the central range. And you guys know very well, xn, right? Xn, this distance, that is the path difference, right? From, see, path difference at the central point is 0. So whatever distance you get here, you'll get the path difference from there, isn't it? So what is the path difference? We can find out. Xn we know. So in this case, y, if I take y, so y is actually given by small d into the distance of y divided by capital D. So this is actually, sorry, this is actually path difference. Okay, this is the path difference. Path difference. Okay, so if I do this thing, look, 2 pi by lambda into path difference. Path difference is actually d. I'm sorry, this is not, I'm sorry guys, this is actually xn is equal to small d lambda by d. Actually this is actually the path difference. Okay, small d into lambda by d. So let us write this. Small d is given, so that is 3 millimeter. Let me write it down here. 3 millimeter means what? 3 into 10 to the power minus 3. Okay, let me write in terms of expression itself. So path difference will be d lambda by capital D. This is the path difference. Okay, just a minute, I'll drink some water and come. Excuse me guys, yeah, I'm back. So I have to put the values here. So what I should do? Three centimeter. Actually, what we know is, see, let me write once again. See, xn is equal to d lambda by capital D and xn plus 1 is equal to, so if I say this is n lambda, this is n plus 1. So kind of that we do. So actually, if I multiply this, path difference will be actually, see, this distance y. Okay, we know this. Okay, y. So this delta path difference will be actually y into this. Okay, y into this vector. Correct. So what is given? 3 centimeter. So this will, path difference will be y into d lambda by d. Okay, so we have to multiply y over here. Okay, so that is the path difference. Okay, so 2 pi by lambda we can actually cancel out. It is the lambda. I'm sorry guys, I think I have just done a small mistake over here. Let me tell you this. Path difference is not lambda. Path difference is given by y d, that means xn d by capital D. Okay, so this is the correct answer. Okay, this is the correct expression for the path difference. So we'll get the phase difference from here, that is 2 pi by lambda into y d by capital D. This is correct. Okay, so this is path difference. I was actually doing n lambda, so I was just mixing up with this. Anyway, you guys know very well the formulas. Okay, so here you know what we have to do. 2 pi lambda right here 5000 10 to the power minus 10. Okay, so this is the one, this is in angstrom. Then you get 3 centimeter, that is 10 to the power minus 2. Okay, small d is 3 millimeter, 10 to the power minus 3, divided by capital D, that is 2 meter, as it is. All right, so let us do it here. What we are getting, so this two I can cancel out, isn't it? Yeah, so I can do that. See here there are 3 zeros. See, I can get here 9 pi into 10 to the power 10 to the power minus 5. So what I get from here, I get 5 into 10 to the power minus 7. So what I get here, 9 pi into 100 over here divided by 5. So this will give you 20. So what I get, that is 180 into pi. 180 pi means, so what is this 180 pi? See, this is actually an even number, right? This is an even number, right? So I can say this will be actually a bright position of a bright fringe. Okay, now let me just do one thing here, just a minute. I think I don't have space over here, so I have got the phase anyway. Let me write this phase over here. Phase is 180 pi. We know the intensity will be 4I0 cos square 5 by 2. Okay, 5 by 2. Okay, so 4I0 cos square, so this is actually 90 pi, and you guys know this 90 is an even number, so even pi will give you, cos of even pi will give you 1, actually 4I0. All right, so this is the case. Let us go to the next problem. Before that, let me just connect the power to my laptop. Yeah, here we go. So this problem is from 6th April paper, first one. Okay, shift 1. Okay, so April shift 1. This question says, in sonometer, fundamental frequency changes from 400 to 500 Hz, keeping the same tension in the strings. Find the percentage change in the length. If the frequency changes from here to here, if the tension is same, then how is the length changing? That means you have to find out the percentage change of the length in the sonometer length. Okay, we know the frequency, you know what you get. Frequency nu is equal to V by 2L, like this, and V is actually square root of T by mu. So this is actually mass per unit length, mass per unit length. Okay, mass per unit length, this mu. See, even though the tension is actually same, but this mu is not going to be the same if the length changes, right? So that's why the V is also different in different length, for different length. Okay, the speed of sound in the string will be different when the length is changing. So that's why I can write, say, frequency mu so nu 2 by nu 1 as I'm sorry, the speed will be the same, but mu is not same. Anyway, I'm just keeping it here. Okay, so let me do one thing. I'll go with directly this L itself. Okay, because yeah, let me just do it. L1, suppose L1 is V by 2 nu 1. So V by nu is nu 1 is actually 400, so it is 400 over here. So V by 800. Okay, so what about L2? L2 similarly I'll get V by 1000. Okay, now look, if I just want to find out what is percentage change or fractional change, so that it will be actually L2 minus L1 divided by, here actually I should not do L2 because you know this frequency is inversely proportional to length. So let me just take the modulus of that. Okay, so mod of L2 minus L of 1 divided by L1. Okay, this is the, and if you multiply 100, that will give you the percentage change in the length. Okay, now let us put this here. So L2 is V by 1000, V by 800 divided by V by 800, and if you multiply 100 over here, so eventually what we'll get, 20 percentage. Okay, if you do this, you'll get that. Okay, this obviously you have to take the modulus of that. Okay, so guys, this was the answer, option C. All right, let us go to the next problem. So this problem says, for what boolean values of a, b, c the given logic gate gives output 0. So this is OR gate, this is an OR gate, this is an AND gate. Okay, this is AND gate. You look, these are A, B, C. So what is the output? Why I get, see, this one, I get A or B. Okay, here I get, see this, it is going here. Okay, this is A or B, and this is OR again, or B and C. This is what I get, isn't it? Look, one thing, if I have this, I can simplify anyway. I can simplify further this as A or B. Let us take common, so I'll get 1 plus C. So anything 1 plus C is 1 itself. So let me write this A or B. Okay, so what I see here, the output depends on the value of A and B. Output depends on the value of A or B. Okay, so I have to get here 0 output. So if I want to have 0 output, I have got y is equal to A or B. So both of them have to be 0. Otherwise, you are not going to get 0 output, right? It is irrespective of C. You have to see the value of A and B. So when I have got both A and B 0, then only I'll get 0 output. Okay. So this is okay. So B, option B is the correct answer for this question. Now this is the last question for today's session. Let us try to solve it. This is also, I'm sorry, this is actually 6th April paper, shift 1. Okay. So the question says thermodynamics. Okay, in thermodynamics, adiabatic process. Adiabatic process, the pressure is directly proportional to cube of absolute temperature. That means this is the thing. What you have to find out, what you have to find out Cp by Cp. You know Cp by Cp means what? That is gamma. Okay, gamma means this one. Okay, so Cp by Cp, this is for a gas. I have to find out where in case of adiabatic process the pressure is related to this. See, I know P v to the power gamma is equal to constant, right? P v to the power gamma is equal to constant, right? Some constant K. Now look, P is for adiabatic process, P is like this. So can I write P is equal to C T to the power T cube? C is some constant. So let me write it C T to the power 3 v to the power gamma is equal to some constant. Since this is constant, I can actually divide this with like K with C and get some other constant. Let me take that as some uh, some C prime or K prime, let us say kappa itself. Okay, this is a constant term. Okay, now I have to find out gamma. But how do you find out gamma over here? This is the relation for this particular gas I have got. But originally what I know, T v to the power gamma minus 1 should be constant. This is ideally, isn't it? Ideally, this is the original equation for adiabatic process. Let me just try to get in this type of form, right? Let me just get in this form. Okay, okay, so at least let me do one thing. Let me do this. T cube v to the power gamma whole to the power 1/3 both side. So this is going to give another constant, so I'm not changing itself. Okay, let me take this as constant itself. Okay, so what I get then, I get T v to the power gamma by 3 is equal to constant. So if I compare with T v to the power gamma minus 1 is equal to constant, some constant. So if I compare these two, I can say gamma minus 1 is equal to gamma by 3, right? Let me write it here. So gamma minus 1 is actually gamma by 3 here. Okay, then what I get, gamma minus gamma by 3 divide that is equal to 1. So what I get here, 2 gamma by 3 is equal to 1, or gamma is equal to 3 by 2. So this is the answer actually. Okay, look it here, Cp by Cp is equal to gamma, and gamma value of gamma I have got 3 by 2. So Cp by Cp will be 3 by 2 for this gas. Okay, So here I'll stop for today. Next class we'll continue with 6th April paper. Both the shift 1 and shift 2 will try to finish. So thank you for your patience. Bye for today.
This conference will now be recorded.